All right, let's go ahead and get started. All right, so we're going to finish up section 5.2 today. I'm pretty sure. Any questions on anything we've done so far, especially with the integration stuff? Okay, so just a reminder, last time when we finished up with found this area underneath this, or really evaluated this integral approximately by thinking about it in terms of the area. So I don't think we actually wrote down what our final answer was, did we? Let's go ahead and do it now, just to be clear. So while I'm doing that, what did we say about this number we were going to get? Is this going to be accurate? It's going to be an overestimate. Why do we know that? Right. So this exactly comes out to be 525 over 36, which is about 14.6. Could we find this area exactly? Yes. In this case, how come?
Because it's linear, you can use all the midpoints and now get it exactly.
Okay, could we do something even more simple? So the area we're trying to find, I'll put it to you this way, you could have found this area in the 6th grade, right?
Okay, just by taking.
So, so we know we can do this without integration or without like calculus at all. But that'll help us confirm what we're about to do. So this was an approximate, and like we just said, this is going to be an overestimate because we're dealing with the right endpoints on a function that's increasing. So we're going to be overestimating. So now let's find this thing exactly. So the only way we really know how to do this is to think about it in terms of, you know, our definition of what an integral is. We're going to take the limit of our change in x. So basically that change in x are the width of each one of our little subintervals. We want to take that thing down to 0 and see what happens. So really what we're looking at is the limit of this sum. So we okay with this? Hopefully looks a little bit familiar from last time. Okay, so let's start filling in the pieces. Let's handle delta x first. So I'm trying to do this with basically n rectangles. So how can I find out how wide, what the change in x is going to be for each one of those small rectangles?
X out of the start.
What's that?
X out of the start.
That's not going to tell me how wide the intervals are. So the xi star bit, that's going to be where the x values are. And then the f of xi star is going to give me the y values that correspond to each one of those x values. So let's back up. How wide is the full interval?
And now it's 5.
It's 5, right? And I'm going to divide that into how many equally wide chunks? N. So that means, you know, for whatever my n is, for however many rectangles I make, the change in x is going to be 5, basically 5 times 1 over n, right? We okay with that? Okay. So that's my delta x. And I think I'm sort of redoing some of the stuff we did last time, but I think it's worth doing because we may not be sure where it comes from. Let's go ahead and set this up using right endpoints. It's not really going to matter if we have infinitely many, but we'll stick with right endpoints because that's mostly what we've done. Now I want to think about what is the first x value going to be. So I really should be calling these xi, x1 star, x2 star, x3 star, x4 star. So where is my first x value going to be if I'm choosing right endpoints. How'd you get 5 over n?
You just go with the first width, your first delta x.
Right.
0.
So each one of these things is delta x, right? Each one of these widths. And if I want the right endpoint, what's the left end of the first interval?
0.
0, right? So if I go 5 over n to the right, then my first endpoints, or my first x value is going to be 5 over n. What will the next one be?
2n.
5, I hear a lot of numbers. So how far to the right am I moving each time? 5 over n. So if I do that twice, it's,
10 over.
yeah, two 5 over n's. So 10 over n. And then,
You don't need to know n to do that, right?
do we know n right now?
No.
No. What's the next one going to be? 15n? I think you meant that. So, yeah, so good question by Solomon. Do we need to know what n is to do this? No, in fact, we're doing it this way because we prefer not to know what n is. So we can set this up now and then we can use whatever value of n we want. All right, so I think I hope 4 is enough data points. Can I generalize this for any value of I? Based on the patterns emerging from those first 4. Set up a table here. When I is equal to 1, 2, 3, 4, x sub I is equal to 5 over n, 10 over n, 15 over n.
5i over n.
How do we feel about 5i over n? Does that work for the 4 we did? Okay, so I agree with it. All right, so that is 5i over n. If that is 5i over n, what is f of? Maybe I should ask this. What is x? What is the xi star? What is that piece in this puzzle here? That's which x coordinate?
Like each, oh, it's the right end.
Okay, so that's what I was saying. It's all of them, right? So these are a specific few. This can really stand for any of them, which is valuable because I'm going to I need to generalize this as much as I can. So if that's what xi star is, what is f of xi star?
F of 5i.
Right. Okay. And why do I know? Why is it the same? Is it always the same? Why for this function or why for this question is this? Right. That is the underlying function here, which comes from this here, is f of x equals x. It's the identity function. The x value is the y value. So, and that is, again, specific to this example. What does f of xi star mean? Like, what is that representing in this process here?
Just for what x star.
Not, so I think we talked about what xi star represents, right? Those are basically all the x values in the sample, right? What does the f of xi star represent? What's that? Okay, I'm sorry. If you're raising your hand or you're gesturing. Yeah, that's the height of all those rectangles, right? So basically what I have now, I'm adding up all these widths times all these heights. I'm adding up a ton of areas. And so let's just fill in what we have here. The limit as delta x goes to 0. By the way, do you mind if I replace this with a different idea? Are we okay that those two things are the same thing? Me saying that the change in x gets arbitrarily small, hopefully that is okay as me saying that the number of rectangles I have is going to get arbitrarily big. Those two things go hand in hand. So from there, what is the summation I'm dealing with? F of x sub I star, which we said is 5i over n, times delta x, which is 5 over n. And if I simplify a little bit, I get this. The limit as n goes to infinity of 25 over 36 times I. Any questions about what we've built so far?
Oh, how do we get to 25 over 36?
I just combined the 5 over n. The 36 doesn't come out. I'm getting ahead of myself. So 25 over n squared, right? So last class period, I said n was 6, right? I had that stuck in my head. So this will be 25 over n squared. As far as the summation goes, what's the variable? It's like the way this sum works, what's the variable?
I.
It's I, right? So I can pull out everything else. As far as the limit is concerned, what's the variable?
N.
It's n, right? But for now, I can do this. The limit, that limit, as n goes to infinity, and I want to slow down and talk about this. I think we had some trouble with it last time because it's still really new. That sum right there, how does that sum start?
1.
So let me make some room here. So the sum, let's just do from 1 to 4 of I. What does this sum equal to, or how do I find it?
1 plus 2 plus 3 plus 4.
And you stop at 4?
Yeah.
Okay, in this case, we stop at 4. So yeah, basically I start at I equals 1, and then I count up by ones. And I think last time I gave you a formula that I don't necessarily need you to remember of what happens when I add the first n numbers together. So I'm going to use that and just replace the summation notation. I know that when I add up the first n numbers, no matter what n is, I get n times n plus 1 over 2. Is this a limit that I can find? Let's clean it up a little bit before I ask you that again. So 25n plus 25 over 2n.
12.5 plus 12.5.
12.5 plus 12 plus 5, 12.5n.
Yeah.
I don't think you said what you meant.
Oh, over.
Yeah, for now I'm gonna leave it like this: 25 over 2 plus 25 over 2n. Can we look at that limit and just see what it is? What's going to happen to that as n goes to infinity? The whole thing goes to 0?
Just in a second.
I was going to approach 25 over 2.
It's going to go to 25 over 2, right? So that should be the value of that integral. Really the only thing, or not the only way, but the biggest way we've talked about integrals so far is areas, right? What's the area of that triangle?
13.5.
13.5?
Or 12.5.
Okay, hopefully it's 12.5, right?
Yeah.
How long is the base?
5.
How high is it?
5.
5. So area is base times height over 2. So that fits, right? So long way to go to get the area of a triangle. But this thing here can be used for, area under any continuous function. Any questions here about what we did with this? How we got this exactly?
So the change in X is called N, right? That's the X.
No, oh, well, those are two different things, right? So for us, the change in X was related to N. They're not the same thing. And just to kind of, hopefully this further highlights how they're related, let's go back to when I gave you a specific N. So last time we ended with there being how many divisions of the interval?
6.
6, right? So that means if I want to divide that interval into 6 equal chunks, I have 5 units of length, and I want to divide them 6 ways. That's 5 over 6. And there's another example, the more general one. I have 5 units of length, and I want to divide them up n ways, n equal ways.
5 over N with delta X equals.
Yeah. Yeah. In this case, yes. I mean, what does it depend on? What does the delta X depend on?
The amount of rectangles on me
The amount of rectangles you want to make is 1,
and the length.
and how big the interval is. So yeah, in this case, the interval was 5 units wide. It can be any size.
So you go from looking for limit of delta X to 0 to N to infinity.
Yeah, is that okay with you?
Yes.
Is it okay? I mean, these things are exactly equal. And I tried to explain it, but if I need to go after it again, I can't. Basically, the delta X is basically how wide each interval is. So that getting really, really small means I'm just dividing into more and more pieces, which is why n is going to infinity. All right, what else? Okay. So some more properties of definite integrals. This is very rarely done, but if you flip these, so let me give you a vocabulary term here. The A and B here are called limits of integration. And basically what that means is they're the left and right ends of the interval that you're integrating. So what were our limits of integration on the last one we just did?
0, 1, and 5.
0 and 5. So basically got what are the least and greatest values of the interval you're looking at. And basically if you transpose those limits of integration, you're going to get the same number but opposite. So I could, based on the work we just did, I could ask you what the interval from 5 to 0 is of x dx. All right, what do you think this one's equal to? I'm integrating a function over some interval of how much width? How wide is that interval?
0.
0. So what do you think the integral is equal to? 0, right? I mean, for right now, we can, hopefully the easiest way to ground what an integral is to you is this area concept. If I don't have any width, I can't have any area.
Well, like English, the integral means the area from here to here of this.
They're not the same. What you just said is kind of like saying the derivative is the velocity. Velocity is a thing we can figure out with derivatives. Just like area is a thing we can do with integrals, but they are not exactly the same. Integrals have lots of things they could be used for. How about this thing? I am integrating a constant over some interval.
That's just A times B.
A times B? Back to area. What kind of area am I going to find if my function I'm integrating is constant? Not 0. I mean, it could have any y value. So let's see. But a constant function graphs as a horizontal line, right? So what kind of area is that? Pretend all my lines are straight. A and B are vertical lines. The x-axis is horizontal. Y equals c is horizontal. So that function or that shape is Maybe the chat knows. It's a rectangle. So Garrett, you're close. So it's a rectangle, right? So how do we find the area of a rectangle? Length. C times, what is the length? You want to say? Yeah, essentially length, height, constant C, times the length, which is just defined by the difference in the where the intervals ends are. Just like with differentiation and really with sigma notation, if I have a constant multiple times a function, I mean, you saw me do this in the last example. I had constants inside my integral and I just pulled them out. You can do the same thing here. Sometimes it's easier to deal with a derivative or an integral. Kind of leaving the constant to the side until you're done. And same with sums and differences. How do we deal with sums and differences when we're dealing with derivatives, for example? And you can do them term-wise. So same thing here. I can absolutely just treat one of them. So provided that what they are joined together through addition or subtraction, then you can handle them and turn it in time. How are we doing?
You go back 1 second.
I can. Oh, maybe I can. Any other questions about this? Okay, so I want to evaluate this integral by talking about it in terms of area, which for now we can definitely think about integrals in terms of area. I think there's only one other way we've talked about integrals. What have we used integrals to do other than doing areas? Didn't we do when we dealt with distances and speeds the other day? I'm pretty sure we did. So this one, I want to find the area underneath this function over what interval, like what x values do I care about?
-32.
-√2. So I want to graph this function. 1 minus the absolute value of x. All right, this is not going to be to scale, but that's okay. So basically the area I'm looking at is shaded like this. Any questions on basically the picture I've drawn for you? Do we know how to find these areas here?
Shape is going to be like this.
Like the values.
Basically, I don't know. Hold on. Now I'm doubting myself. No, never mind. I'm okay. Oh, basically, yeah, I plugged in a few values in my head.
So
1 minus 2 is -1. Oh, I had the absolute value in the wrong place in my head, didn't I? Starting over. I wanted the absolute value to wrap around the whole thing. So let's do this more carefully. When x is equal to -3, where are we? 2. Negative, how about x is -2? -1? When x is equal to 0. Oh, I missed one, didn't I? When x is equal to -1, that is 0. X is equal to 0, I get 1. When x is equal to 1, I get 0. And when x is equal to 2, I get -1. All right. All right, that makes this a lot more interesting. So there's my graph, right? All right, so I got to think about this in terms of areas. So how should we proceed? Isabel?
It's like dissecting it, so areas between -3 to 1 is gonna be subtracting whatever it is.
Okay, so let me stop you right there. You're saying to do that area first, right?
Yeah, but it's gonna be negative
Why?
because it's underneath and we're subtracting.
Okay, so let's do this. We'll call this thing area 1. Let's find that area and then we'll move on. What is area 1 equal to? I'm getting 2, is that right? Okay. So area 1 is equal to 2. For now, I'm going to call them all positive. All right, for area 2, let's give x values with these. So that goes from -3 to where? -1. Our next interval should be what? From -1 to what? +1. How big is area 2? Should just be 1, right? Base is 2, height's 1. Okay. And then area 3 should go between 1 and what other x value? 1 to 2. And what's that area going to be? Should be 1/2, right? All right, so if we're going to chop up this integral into these many pieces, basically what we're looking at is this. The integral of this function, 1 minus the absolute value of x, is equal to, so which areas are going to be positive, which ones are going to be negative?
Area 2 is positive and area 1 is negative.
Okay, so -a1 plus a2 minus a3, which is equal to 2 plus 1 minus 1/2 minus 3/2.
But we can get the values for the area just by 1/2 base times height.
Yeah, they're all triangles, right?
Yeah.
So yeah, so we're interpreting in terms of area. So if this was like a parabola or something, we'd be stuck. We don't have easy formulas for those kinds of things. Any questions here? Yep, I was wrong. Should be fixed now, right? Okay, I hope so. Otherwise, it's going on the internet like that. All right. Here's another property whether or not you realize we kind of talked about this. So we have one integral. So same function, both integrals, right? So the integral from a to b of this function plus the integral from b to c of that function. Can we say anything more specific about that? So if I draw a picture,
So we'll from A to
C, right?
C, yeah, A is right.
Why would it be the, so you're saying, say again, what you said?
Same interval, but from
A to B?
A to C. I don't listen to me in letters.
Okay.
Yeah, because you're adding.
Right. What allows me to combine those like that?
Because if you're taking, it's the common B.
Okay, so that's the thing I wanted to make sure we had down. Is if it was from A to B and then from C to D, would I be able to? No. Okay, good. So go ahead.
I was gonna say, would it also be, would that same thing apply if it was G of X on the second one?
Let me draw this. So
It was a different function.
let's talk about f of x first. So just a single function here. Basically, if I find this area and then this area and add them together, is that the same as me finding the area of the whole thing at once? Okay, so if this is a single function, hopefully I've convinced you that that's fine. What if, yeah, what if it's two different functions? Can I make that generalization? So I think what Christopher is saying is this. Can we say anything it's specific about that? G of X could be, yeah, it could be anything, right? So it does have to be the same function. I have to be integrating on the same function for that to be true. And just to be clear, what else do I have to make that? So basically make that combination happen? Yeah, they have to, basically the middle of that interval, really A to C is one interval, right? So basically divide that so that B is the right end of one interval and the left end of the next. So because of that, can we answer this weird thing? I want to find the integral from 0 to 6 of 3fx minus g of x. Based on the things we know.
-4. No.
-4. How'd you get that?
You add the integrals of 0 to 4 and 4 to 6 is 5, and then it's subtracting that from. Wait, so what's 5 by 30?
You're trying to slide off a lot of steps at once. So let's go slow. What's one thing we can do right now? Like what's one small conclusion we can do?
Add in f(x).
Okay, so if we add so I gave you some data about some integrals of f of x. And you're saying I can add these together?
Yeah.
Why can I do that?
Because they share the 4.
They share the 4. So this right here is equal to the integral from 0 to 6 of f of x dx. And that's equal to what? Equal to 2 plus 3, which is equal to 5. So are we okay with this idea? The integral from 0 to 6 of f is 5? Okay. So yeah, clearly the thing I want to answer has to do with that interval, so that was a good move. What else can we say? Why can you do that? Right. And if I bring them back to area, if I only had to find the area underneath the function and you found it, it's like, all right, well, let's take all the y values and triple them. What happened to the width in that case? Nothing, right? What happened to the heights? I tripled them. So stands to reason your area should then triple as well. So that fits. So if I want to find the integral from 0 to 6 of 3 f of x dx, That's equal to 3 times the integral from 0 to 6 of f of x dx, which is equal to 3 times 5, which is 15. So now what?
Just minus
15
5.
minus 9.
Why 9?
Because that's the entire interval of g of x dx.
Right. So now I think we can go the whole way.
Do you need the integral sign in front of it again? In front of the GX?
Not if I do this. And really, if you want to be totally clear, you should do that. It's kind of understood even without it. But yeah, it's probably a little more complete to put parentheses everywhere. But to answer this a different way, you're not wrong to do this. It's not very commonly done that way, but it's not wrong at all. So this is equal to 15 minus 9. Actually, let's make this real clear. We good there? All right. How about this thing? Can I say anything about the integral from 15 to 27 of that function?
7.
How'd you get that?
If the area from 0 to 27 is 10, and from 0 to 15 is 3, the leftover part is 15 to 27, so you can just subtract whatever 0 to 15 is.
Okay, so let me try to convince you a couple different ways here. First, I'm going to draw totally not to scale area thing. So really integrating, let's just look at all the x values I care about from 0 to 27, right? I have a function that looks like, who knows? I know that this area right here is, the whole thing is 10, right? But if I divide this into a couple of pieces, that's not going to be clear. This area right here is 3, right? And if the whole area is 10, this remaining area has to be 7, right? Does that make sense? Okay. This is also basically what we looked at just a minute ago. So the integral from 15 to 27 of f of x dx, we'll kind of fill in some blanks here. So what integrals do we know about? Or sorry, what intervals do we know about? We know about 0 to 27, and we know about from 0 to 15, right? And this is a relationship I just had on a slide. I don't think it looked just like this, right? I think the version I gave you was a sum. But if we rearrange a little bit, I can add this third term to both sides and get this. The integral from 0 to 15 of f of x dx plus the integral from 15 to 27 of f of x dx is equal to the integral of what interval of the same function? 0 to 27, yeah, the entire way. So yes, we can say that integral is equal to 7. Any questions there? Okay. All right. I want to do this. Yeah, I'm gonna go ahead and skip the Riemann sum one. Let's just skip it right onto example 9 here. I want to find that area, or I want to find this area, this integral by thinking about it in terms of an area. So the function, what's the function of trying to find the area underneath?
16 x squared.
Okay. Do we know how to find areas like that? I mean, there's very few things at this point you can do with integrals. So what other ways do we know how to find areas?
Other shapes.
Other shapes, right? So yeah, basically geometry is, your biggest weapon right now. What kind of shape is that?
A circle.
Is it a circle?
I'm trying to remember. I remember a function back in like 7th grade that was like, I mean, it's definitely a curve.
It's definitely curved, right? So here's the function, right? Do you remember what the equation of a circle looks like?
It was really similar to that. You know, like it was x squared with a root over it.
So yeah, x squared plus y squared equals a number, a constant is a circle, right? Let's think about it this way. Let me draw a thing. Basically what I have here, I have this kind of graph where, no matter where I say x and y are, if I take x and square it and y and square it, and then I add those together, I get a number. So basically I'm taking my horizontal distance, squaring it, my vertical distance, squaring it, and no matter where I do that, I get a constant number. Basically that's a radius, right? My distance from a center is always going to be the same thing. So what is my radius in this case then? This is x, this is y. What does this thing look like to you? I'm taking the horizontal distance squared, a vertical distance squared. It's a Pythagorean theorem, right? So really I have x squared plus y squared equals whatever that radius is squared. So in this case, the radius is equal to 4. All right.
Real quick, I have a question.
Absolutely.
So the circle, is that even a function though? It doesn't do the one-to-one.
So note that. So you asked a couple of things. Is this thing right here a function? Radical like 16 minus x squared?
Yeah.
Just this piece of it is.
Okay.
Because if it was plus or minus, I'd have a problem. But the way that's written, like the square root function only gives back positive or non-negative numbers. So, and that's one thing we need to think about here is, I don't think I can do this. All right, the area is equal to pi r squared, right? 16 pi? Is my area 16 pi? So now that we know what we're looking at, we're looking at a circle of radius 4, right? But are we looking at all of the circle? How much of the circle are we thinking about?
Half of it. Oh, wait.
Here's my circle. We could certainly find the area of the whole thing, right? Jarek says what half of the circle are we going to find?
The left half.
Oh, I should have broken that up. You're saying we're finding that area.
Yes.
I don't totally agree. You're getting closer. Clearly it's not the right half, right? So why did you get rid of the right half?
Because it starts at -4.
Starts at -4. And it ends where?
At 0.
Okay, so clearly you're not looking at anything to the right of the y-axis. Isabel?
Would it be just 1/4 of the circle and it'd be the top one because it?
That's right. So, and this is kind of what Christopher was asking about, is this going to be a function? So let's answer that question. Is that thing that's up there right now a function? No. So we know that, integrals only work with things that are defined to be functions. So yes, we are looking at specifically this area here. And another way to say that, that square root function, basically what we have here is f of x equals the square root of 16 minus x squared. That is only going to give us non-negative values.
So then the area is 4 pi.
4 pi, right? So the area is a quarter of a circle. So no, but the area is pi r squared divided by 4, which is 4 pi. How we doing? Okay, that's all I got for you. So that was all for 5.2. I said on Canvas we'd have time to review. We don't really, but so just looking ahead, test is on Monday. Friday, we're not going to start 5.3. So Friday, bring to me whatever questions you have, and we'll talk about whatever you want to talk about. I put a pretty long list of problems from the book to look at, which will be good practice. I really recommend looking over those and at least knowing what you want to talk about on Friday. So come to office hours tomorrow on Friday. Bring questions to class on Friday. I don't think I'm going to be able to do a review session on Zoom this time, but my email is always open. Plenty of time for you to ask questions. Solomon?
What are we gonna do after the test? Because we only have 5.3 and 5.4 after that, right?
Yeah, they're longer than you think. So,
And then those would be on the final.
so the final will cover everything and those 2 new sections. I'm hoping we have at least a day or two to just Q&A type review stuff. But this, so we're going to cover 5.3 and 5.4. Calc 2 starts with 5.5. So I want to make sure that we talk about 5.3 and 5.4 as long as we need to, so you can hit the ground running in the fall.
How long is the final? Do you know?
In terms of time,
Questions or any?
last semester mine was 15 questions. So you have twice as much time to do it, and it's not twice as long. So don't let that don't ease up too much, but
Is the date for sure, whatever's on the calendar?
May 5th in this room, 7:10 as well,
For how to, you're using the same test, right?
for all the way through Calc 3.
Oh, okay, so-
Yeah. Anything else? All right, I'll see you all Friday.
The first line of this thing, like a is equal to, what did you write here?
Oh, that's pi r squared. That's the area of a circle.
And then what?
So I put a question mark over this
Okay,
because this is something we were not sure about.
okay, so we just.
We ended up
A
rejecting
is
it.
equal to pi r.
Yeah, so I was using this to ask the question, are we really finding the area of the whole circle or just a portion of it?
Why didn't we use pi r square over 4? Because we're taking 1/4 of a circle, right?
Well, we did, we eventually did.
Oh, okay, okay.
Yeah.
And then we integrated it, or?
No, I mean, this is not a function right now.
Mhm.
Right now, the only kinds of functions you can integrate are like constants, linear functions, parabolas.
Okay,
So we did not do an integral here. What we know that integrals give area, and we utilize the fact that this graph is a circle to find the area that way. So this is not something you
Oh,
can,
okay,
so we didn't actually use like the formal integration
Okay, so
process here.
integration was not connected to it, I guess.
Only in that integrals find area and we found an area.
Okay, that's the best question.
Yeah.
So it means I'm taking from 0, 1, 2, 3, 4, 5, and I'm taking the areas. Is that correct?
Yeah, but basically, and so you have 0, 1, you're kind of counting that by ones.
1, 2, 3, 4,
Yeah,
5.
really, when you're doing an integral, like you're doing all the values between 0 and 5, all the real numbers between 0 and 5.
Real numbers
As in, like-
decimal values as well?
Anything.
Like 0.01 as well.
Yeah, and all the rational numbers, all the irrational numbers, an infinite number of values between 0 and 5.
Okay, so it's restricted between 0 and 5, but there are infinite values.
Right. And I just did between 0 to 5 for that one example. I mean, our intervals can be,
Yeah, that's why I was confused, because dx means our x is like really small and.
yeah, basically delta x, so the uppercase delta we use, that's like a measurable change in x. Dx is this limited thing. This is the end process of an infinite. Sorry, it's the end result of some infinite process.
But when we are doing the math, we use like 1/5 and plus 2/5 like this, right?
That comes from the summation notation. So here's this thing right here. And I think here's what I'm hearing you say. I think you have this idea that these two things are equal,
Yeah.
and they are not until you do this. These two ideas are only equal when I take this. So this right here is just me adding up a bunch of areas of rectangles, right?
Mhm.
The only way this thing right here becomes equal to this integral is if I see what happens when I let my number of rectangles get very, very large.
What is this n?
That n is the number of rectangles, the number of like partitions you put on this interval.
Okay. So in this one, we don't have any limit, like 0 to 5. We know
You
that
kind
we are
of
gonna
do.
stop at 5, but why do we stop?
It's
at
baked into this delta x. So if we go back a few slides here. So yeah, for here, we said that delta x is equal to 5/n. And the reason it's equal to 5/n is because the whole interval is 5 units long, and I'm dividing it into n pieces.
What do we see with the axis?
Not 5/n.
Oh. Okay. So it's given in the question or?
So I gave you this interval, right?
Yeah.
So that width is 5.
Okay.
So the whole width is 5. So if I'm going to divide it into n equal pieces,
Each piece.
each piece is 5/n. So no, it's so in the sigma notation, whatever this interval is, the interval from 0 to 5, it's not as obvious as it is here, but it's captured in this.
Okay. Yeah, I think I got it.
Okay, I mean you'll make a little more progress each time. The integral is it's a difficult thing to get your head around, and we just started doing it.
Thank you.
Yeah, of course.